Imagine a yellow bead sliding down a road between two movable walls. The blue wall rises, the coral wall falls, and the road becomes narrower. Near one green gate, both walls meet at exactly the same height. Where can the bead be when it reaches that gate? It cannot jump above the top wall or tunnel below the bottom wall. So even if the bead wiggles wildly, the closing walls force its destination. That simple trap is the entire intuition behind the squeeze theorem. In the next few minutes, we will turn this moving picture into a reliable limit tool. Then we will use it to tame one of calculus's wildest oscillating graphs. Let us slow the picture down before bringing in any symbols. Far from the gate, the corridor is wide, so the bead has many possible heights. Halfway there, the walls are closer, and those possibilities shrink. Very near the gate, the remaining vertical gap is almost invisible. Notice what matters. We never need to predict the bead's exact path. We only need a lower wall, an upper wall, and a shared meeting point. Each step toward the gate removes more wrong destinations. The walls do the hard work. The bead merely obeys the trap. Keep that mental action. Close the corridor, then read the forced destination. Now give the three paths names that match their jobs. Call the blue lower path g of x, the yellow middle path f of x, and the coral upper path h of x. Near an input called A, the blue path stays below the yellow path. At the same time, the yellow path stays below the coral path. That is the visible meaning of g of x less than or equal to f of x less than or equal to h of x. Next, both outside paths approach one common height, which we call L. The theorem says the trapped middle path must also approach L. The inequalities build the corridor. The matching outside limits close it. Those are two separate checks, and we need both. There is one subtle detail. A limit describes approaching the gate, not necessarily standing on it. The middle path may have a hole exactly at x equals a. It may even place a stray dot at a completely different height. Neither change affects the nearby corridor. As x moves closer to a from either side, the bead is still squeezed toward L. So the value f of a can be missing, different, or perfectly ordinary. The limit only asks where nearby values are being forced. This is why a graph can look broken at one point while its limit remains certain. Focus your eyes around the gate, not only on the dot at the gate. Here is the proof idea without a wall of formal language. Draw a thin green target band around L. Because the blue path approaches L, it eventually enters that band. Because the coral path also approaches L, it eventually enters the same band. Choose a neighborhood close enough that both statements are true together. Inside that neighborhood, the entire corridor lies within the target band. The yellow path is trapped inside the corridor, so it lies in the band too. Make the target band thinner, and we can move closer to the gate again. No matter how much accuracy you demand, the same trapping move works. That is the logical engine of the theorem. Now meet the graph that makes direct substitution feel useless. Consider sine of 1 over x as x approaches 0. The input 1 over x grows without bound, so the sine wave oscillates faster and faster. Zoom in, and instead of settling, the graph keeps filling the space between -1 and +1. This function has no limit at 0, but multiply that restless wave by x squared, and something dramatic changes. The oscillations remain, yet their vertical envelope collapses toward 0. We do not need to follow every wiggle. We only need to build the two walls around all of them. Start with a fact we already know from the sine wave. Sine of anything always lies between -1 and +1. Near 0, x squared is non-negative, so multiplying preserves the inequality directions. That gives -x squared below x squared sine of 1 over x, and positive x squared above it. On the graph, these are two parabolic walls, one opening up and one opening down. The yellow oscillation must stay between them. Both walls approach 0 as x approaches 0. The corridor therefore pinches shut at the origin. By the squeeze theorem, the yellow function's limit is 0. Let us test the conclusion at several shrinking input distances. When the distance from 0 is 1/2, the oscillation can have magnitude at most 1/4. At distance 1/10, its magnitude is at most 1/100th. At distance 1/100th, The allowed magnitude is at most 1/10,000th. The exact sign values still bounce unpredictably, but the maximum possible error collapses predictably. That distinction is powerful. We control the size without controlling the sign or the wiggle. The shrinking envelope supplies certainty where the middle formula looks chaotic. A squeeze proof is often really an error-bound proof in disguise. Try the same mental move on x times sine of 1 over x. Pause for a moment and ask, what simple quantity controls its magnitude? Since the sign factor never has magnitude above 1, the product's magnitude is at most the magnitude of x. That statement creates a lower wall at negative absolute x and an upper wall at positive absolute x. Both walls approach 0 as x approaches 0. So the middle product is squeezed to 0 as well. The envelope is now a sharp V rather than a pair of parabolas. Different walls, same mental action. Bound the wiggle, close the corridor, name the destination. You have just solved a second oscillating limit without tracking a single oscillation. The middle function does not need to oscillate, and the destination does not need to be 0. Suppose a complicated quantity is trapped between two simpler estimates. If both estimates approach 5, the trapped quantity approaches 5 too. The same logic works for one-sided limits and for inputs moving toward infinity. For example, imagine an awkward average trapped between 10 minus 1 over n and 10 plus 1 over n. As n grows, both bounds approach 10. The average must approach 10, even if its exact formula is unpleasant. Squeezing is therefore a general comparison strategy, not a special sign trick. Whenever exact calculation is hard, look for easy upper and lower estimates. Before using the theorem, watch for 3 common mistakes. First, checking the inequality at only a few sample points is not enough. The ordering must hold throughout some whole neighborhood around the input. Second, one wall approaching L does not force anything by itself. Both outside limits must exist and match. Third, multiplying an inequality by a negative expression reverses its directions. That is why absolute values are often the safest way to build symmetric bounds. Check the corridor, check the shared destination, and check any sign changes. If those checks pass, your conclusion has a solid foundation. Return to the yellow bead and the 2 closing walls. The middle path may bounce, break at the gate, or resist direct calculation. None of that matters once a valid corridor closes on one height. When you face a stubborn limit, use this 4-step checklist. Find a simple lower bound, find a simple upper bound. Verify that both approach the same value, then squeeze. For x squared sine of 1 over x, the parabolic walls closed at 0. For x sine of 1 over x, the absolute value walls did the same. The squeeze theorem turns uncertainty in the middle into certainty from the outside. You do not have to catch every wiggle, you only have to close every escape route.